Hello, welcome back to Organic Chemistry 2341. We're going to continue on with chapter 8, alkenes and alkynes. Okay, so you might have noticed we're starting to get really into the chemistry things, and we're going to learn a lot about trying to organize our thoughts related to this particular topic. We have a lot of different reactions, they have several different mechanisms, and we have to worry about regiochemistry and and stereochemistry. So we have to be careful about keeping these in track. So what I will be doing and what we'll be doing in the SI sessions as well is we're going to start making reaction tables. Okay, we're not going to do that today, but we're going to start doing that next week. And so these reaction tables you're going to be using for number one, the rest of the semester to help organize your thoughts. And then you can use them next semester to remember all these reactions after you've had a long summer. So this is going to be a good thing for us to do. But what I want to do now is go ahead and share my screen. Let's see if it's popping up. There it is. Okay. Again, the homework is open now for that. There are two sections of homework, 8.1 and 8.2, and then we'll move on to chapter 9, which is NMR spectroscopy. Okay, so let me go ahead and begin with the overview slide. Don't let this slide scare you. Okay, this is all the stuff we're going to learn in this first half here. And what we're going to see is that each reaction has a regioselectivity, meaning the group we're adding is going to go to a specific location, and it has a stereoselectivity or a stereochemistry where it is adding either to the same side of the double bond or the opposite sides of double bonds. And so those are the things we're going to have to pay attention to with each and every one of these reactions we're going to do. Okay, so you might want to start thinking about, this reaction does this mechanism and does syn or anti-addition. So that's what we're going to start defining as we move through this chapter. Okay. So the first thing I want to talk about is the addition of hydrogen halides to alkenes. Okay. Now remember, we made an alkene by using a base and removing a hydrogen and a halide. Okay. So this is the reverse reaction. Okay. So in general, we're going to take the hydrogen and add it to one of the carbons, and we're going to take the halogen and add it to the other one of the carbons. And we are going to see the reaction is specific about where the hydrogen goes, and it's specific about how the halogen comes back onto it. Okay. So the overall reaction is shown here at the top, where it's just we're getting rid of the double bond and we're making two new sigma bonds. We're switching hybridization from the sp2 carbon to the sp3 carbon. And so we're going back to the tetrahedral straight. So the first step is we actually have the alkene double bond is acting as the nucleophile. It has a lone pair in that double bond. It has a pair of electrons, in that double bond. And it's going to react with the electrophile, in this case, the positively charged hydronium ion or the hydrogen in our system. That's going to go through a carbocation intermediate. Okay. So with a carbocation, remember that's an empty p orbital. Then our nucleophile comes in and attacks either the top or the bottom to generate our final product. Okay. So that's the general idea here. And let's look at that reaction diagram. Okay. So to get to that transition state of doing the proton transfer, it takes energy and gets into our position where we're starting to form our carbocation. In the intermediate here, that's where we form the carbocation. Okay, so wait a minute. We're forming a carbocation, and we're going to want to form the most stable carbocation. So the most stable carbocation is what's going to control our regiochemistry. Where the hydrogen goes in the beginning transition state determines where that carbocation is. And therefore, that is what we're going to be looking for, that carbocation stability. The next one is a transition state where we have the nucleophile coming in at the top or the bottom. And then, of course, it makes a nice sp3 hybridized carb bond, and those have less potential energy. So the reactions are net exothermic. Okay. So there are two nucleophiles. Yes, the first thing that's a nucleophile is the alkene, because it has two electrons in that pi bond. The second nucleophile is our halogen ion after the proton has been transferred away from it. Okay, so if we think about it right here, the first step is transferring the proton to the alkene. Okay, so that means the more acidic that proton is, the faster it's going to be transferred to the alkene. Therefore, our order of reactivity is the most acidic to least acidic. HI is first, HBr is second, HCl is third, HF is last. Okay, so this reactivity is directly related to how acidic that proton is, how likely that proton is to be transferred to that pi bond. Okay, so if we form the carbocation, we want to, when the hydrogen adds, form the most stable carbocation possible. And we learned that carbocation stability was the tertiary is more stable than the secondary, which is much, much more stable than primary or whatever. So that means when the hydrogen is transferred, it's going to be transferred to the carbon with the most hydrogens. Okay, it already has hydrogens. We're going to add another hydrogen to that. And when we do that, we form the most stable carbocation. And this is called Markovnikov's rule. Okay, so Markovnikov's rule is the carbon with the most hydrogens gets the hydrogen. Okay, and if we look at that, we can see why, because that if the first step is the transfer of this hydrogen to that double bond, it's got to choose which carbon is going to have that carbocation. In this case, we would have, oops, where'd it go? In this case, right here, we have a tertiary carbocation, the most stable carbocation we have. Okay, so that molecule is happy. It has a nice low transition state because it's forming a relatively stable intermediate. Okay. However, if we transferred the proton to the other side, we'd end up with a primary carbocation. And therefore, it does not happen. We're not going to form the transition state that allows that primary carbocation to happen. And therefore, we do not form that product. Okay. So now that we have our carbocation, our halogen can come in from the top or the bottom to form an sp3 hybridized sigma bond with our product. And so we, again, go from our double bond to all sigma bonds at the end of the product. Do we understand Markovnikov's rule and why the hydrogen always goes to the most hydrogenated carbon of the alkene? Just making sure my mic's on there. Okay. Okay, so it has everything to do with the energy of the transition state. As you're starting to form that, the transition state, the energy to make the transition state of the less stable carbocation is higher, takes more energy, and therefore it's a slower reaction. The formation of the partial formation of the transition state where we're starting to form our partially positive carbon on that more substituted carbon is a lower activation energy and therefore a faster reaction and is our primary, if not only, product from this reaction. Okay, so the partial formation, that partially positive formation during that transition state is the driving factor to tell us which carbocation is formed. All right, so that's with an acid. I mean, that's with HI and HBr and HCl, okay? But that's not the only addition product we can do. We can also do an acid catalyzed hydration, okay? And when we do an acid catalyzed hydration, as the name suggests, we have to have an acid catalyst, and we're gonna add water across that double bond. So we're gonna have a hydrogen add somewhere and an OH somewhere, okay? So I think we have an idea of which one is going to add to which carbon. Okay. So in the first step of the mechanism, the first step is to protonate the water, okay? Because that makes it a very easy proton to deliver, because if you think about it, the pKa of hydronium ion is like -2. Sulfuric acid is also around that same place. And so it's very acidic, and it adds to the double bond the hydrogen first. Okay, so because it's adding to the hydrogen, the hydrogen to the double bond first, it's going to form a carbocation, and it's only going to form the more stable tertiary carbocation, which means the next step is the water coming in as a weak nucleophile has to come in the top or the bottom to share its electrons with that carbocation to make our new bond. However, unlike in the acid halide, the reaction is not over yet. We have a protonated alcohol, so we have the oxonium cation, and therefore we have to lose a proton, so we have a neutral molecule, and we lose that to water as a weak base. And when we lose it to water as a weak base, we have regenerated our catalyst right here. So it only takes a drop of acid to do this and a lot of water. Okay. Why do I say a lot of water? Well, didn't we make an alkene using an acid catalyzed system? Didn't we took concentrated sulfuric acid and heated it up and it lost water to make the alkene? Well, that's true. If you have concentrated acid and or you remove the water as you go through the process, you can turn an alcohol into the alkene. However, if you add more water and just use a drop of acid, now water is the major driving force and it drives the alkene all the way to the alcohol. So the acid catalyzed hydration and dehydration of the alkene to the alcohol and back and forth is reversible, but you can force it to the product you want by controlling the amount of water in the reaction. Okay, does that make sense? Again, this is the same mechanism. We're forming that carbocation. And what we'll learn here is because the nucleophile comes in at the end, at the top or the bottom, that we can get a mixture of syn products and anti-products, okay? So syn is when you add both things to the same side of a double bond. Remember, that's a planar molecule. The pi is above there. You're adding syn, both of them are going on the same side of that. And then when they convert to their tetrahedral state, you can see they're on that same side. Anti is when you have one come from the top and one come from the bottom. Both of these reactions can do either because there's no telling whether it's coming from the top of that empty p orbital or the bottom of the empty p orbital, okay? So that means our reaction is regio-selective because the hydrogen always goes to the more hydrogenated side, but stereochemistry-wise, it's a mixture. It's a mixture of syn and it's a mixture of anti. Okay. So that's just the more detailed mechanism there. Okay. So we've added water to it. We've added acid to a double bond. Let's add bromine or chlorine. Let's do a halogenation reaction where we're adding it there. Okay. Now I'm going to tell you now, it has a different mechanism. Okay, so when we do this addition of bromine to a double bond, you get one bromine on one carbon and one bromine on the other carbon, and they add in the anti configuration. Okay, so like, okay, why? Okay, well, let's figure this out. Okay, so in this case, the lone pair, the pi bond acts as our nucleophile again, polarizing the bromine-bromine bond. Remember, the bromine-bromine bond is not polarized. Both bromines have the same electronegativity. So by hitting it close to those electrons in the pi bond, it starts to polarize the molecule and generates a partially positive bromine and a partially negative bromine. Okay. That's the key step in starting here. But as it does that, we see a difference in mechanism. Okay. So in the case of the mechanism of using bromine, because we're polarizing that halogen bond, we end up making a three-membered ring, a bromonium ion or a chloronium ion that sits on one side of the double bond or the other. So when it comes in, it's just going to sit, share both of those electrons and stay there. Well, you can draw a resonance contributor like here. The fact that you have the lack of an octet makes it a less stable resonance contributor, meaning this is our more stable resonance contributor. Okay. This is key to the mechanism because this changes our way that the other bromine comes in and interacts with it. Okay. So we have polarization of the bond. We have one of the bromines that was partially positive. The other bromine took the electrons from the bromine-bromine bond, and now it's a nucleophile. Okay? So what happens next? Well, that nucleophile acts as a nucleophile, but it has to attack specifically on the opposite side of the alkene because the bromine is blocking the top. Because the bromine is blocking the top, it has to come in from the bottom, meaning that the halogenation reaction is an anti-only reaction. And because it's an anti-only reaction, that's important to note that there is stereochemistry associated with this. So in this case, when we do that addition here, we can have it come in and attack one. So if the nucleophile comes in and attacks this one, we get this isomer here, where the bromine is on that adjacent carbon. And if it attacks on the other side, right here, that gives us this product here because the bromine is attacking on this other carbon. Notice the bromine that was on the top was the one that formed the bromonium cation, okay? And the bromine on the bottom is the one that was the nucleophile. Okay. So by knowing that we form this blocking group on the alkene, it tells us the reaction has to be anti-addition coming in from the opposite side of the double bond.
Okay. I have a question.
Yes.
So you said that halogenation is anti only, and then acid catalyzed hydration is syn and anti.
Correct.
And then, so what about hydrohalogenation? That's just
Okay.
Markovnikov?
No. Markovnikov is where the hydrogen goes. That's the regiochemistry. The syn and anti is the stereochemistry. And in the hydration reaction, it formed a carbocation, just like the hydrohalogenation reaction. That means if it forms a carbocation, it must be a mixture of syn and anti.
Oh, okay.
Whenever you form a carbocation as an intermediate, you form that syn and anti because it can come in either direction.
Okay, I understand.
All right, good questions. Okay, so if we did form a carbocation, we would see a mixture of products. We would see a mixture of syn products and anti products. And the fact that we don't see any syn products at all tells us it must be going through a different mechanism. And our proposed mechanism of the bromonium cation satisfies all of the things we have on our product ratio. So we only have anti-addition, and therefore we know it doesn't go through that carbocation. And it does go through the bridged polonium ion. Okay, now we can complicate things a little bit by adding water to our halogenating reaction, okay? So the only thing that's different here is what acts as the nucleophile on the second step. The first step is going to be the same. The alkene is the nucleophile. It's going to polarize the bromine-bromine bond and create the bromonium cation, the bromonium three-membered ring. Now, in the presence of water, the water can act as a nucleophile, a weak nucleophile. So if you have a lot of water in there, you can actually have the water react as the nucleophile and give you what we call a halohydrin, or the halogen with an alcohol next to it. Okay. Now, if the bromine reacts as the nucleophile, then we're going to end up with our product that's a dibromo compound. But in the presence of a large amount of water, there's going to be more instances where water hits. So if you're using water as a solvent, right here, water as a solvent, you have a whole bunch of water around there. It's more likely to hit than having the bromine come in as a nucleophile. And therefore, your bromo alcohol is your major product, okay? And because we form that bromonium cation, you only get anti-products, okay? Questions? Okay. So it's almost the same mechanism, except you having water act as a nucleophile instead of the bromide ion. Okay, so that gives us some ability to think about regiochemistry now, okay? So if the alkenes react in a Markovnikov's way, do we see that kind of favoritism in our halohydrin reaction? And actually, it turns out we do. Even though the bromonium cation sits on top, and that's our telling us whether it's syn or anti, those two bonds to the two carbons are not exactly equal, okay? If the carbons were both primary carbons or secondary carbons, they would have fairly equal bonds. However, if we have a difference in substitution, like this one is a tertiary carbon and this is a primary carbon right here, we're going to see that the bonds to bromine are not going to be equal, okay? In fact, it'll be a little bit polarized in the system. And if one of those two carbons is going to be more positive than the other, meaning the electrons are being pulled to the bromine and we have a partially positive charge, that partially positive charge is going to be on the more substituted carbon. So if the partially positive charge is on the more substituted carbon, that means it's more likely to be attacked by our nucleophile. In this case, we're attacking with alcohol, meaning we're going to get a specific regiochemistry in our halohydrin reaction or the alcohol version of the halohydrin reaction, if we have a difference in substitution pattern on our carbon. Notice in the example we used before, we just used cyclohexane. So both of these carbons would generate a secondary carbocation or a secondary partially positive carbon. So there's no preference on where that OH ends up. However, in this example here, we do have a more substituted carbon. And in this case, the last nucleophile, the water or alcohol, is going to attack the more substituted carbon, giving you your major product. But this works best if you have a primary carbon and a tertiary carbon. You're going to almost always have all of it on the tertiary carbon. Okay, questions on that? So our regiochemistry can be predicted by carbocation stability or the partially positive charge found in our intermediate. Okay. So now let's go to a different reaction, and the reaction reacts in a little different way, okay? So in this case, we're gonna do what we call hydroboration and then oxidation. And when we do that, we add boron across the double bond, a boron hydrogen bond across the double bond, and then we take it and oxidize off the boron, giving us an alcohol. So those are the two steps. We have to do the hydroboration first, and then we oxidize off the boron to give us our alcohol. So the first step in the reaction is regioselective, but it looks like it's anti-Markovnikov's, okay? It's anti-Markovnikov's because it puts the hydrogen on the more substituted carbon, okay? Write this down. Hydroboration is anti-Markovnikov's. The hydrogen is on the more substituted bond. And what's cool is that you have, in this case, we have borane, which is the BH3, and a THF is the solvent, and it actually makes a complex. It'll react once for the first boron hydrogen bond, but it'll keep reacting until all those boron hydrogen bonds are gone. So you only need one equivalent of your boron for every 3 equivalents of your alkene. So that forms actually a stable product. You can isolate this and you can isolate this and do stuff with it. However, if you want the alcohol from it, You take peroxide in basic water here, and you'll generate 3 equivalents of that alcohol from that system. Notice that this is the anti-Markovnikov alcohol. The alcohol is on the least substituted side. That is completely backwards from the acid catalyzed hydration. Okay. So what do we do with this? Okay. Well, we can use it for regioselectivity. Let's say you wanted a primary alcohol and you had a disubstituted alkene. Okay. If you use the acid and water treatment, you would get the tertiary alcohol and only the tertiary alcohol. Okay. But by using the borane, it's going to selectively react with the least substituted side. And when we oxidize that boron off, we're going to get our alcohol on our least substituted side. So now you have a selectivity of reagent based on the product you want. Okay. If you want the primary alcohol, use the borane. If you want the tertiary alcohol, you use the acid catalyzed hydration. So why? Okay. Well, as it turns out, it's technically actually following the rules of the system. Okay. But let's talk about the stereochemistry first. Okay. The stereochemistry of this is that it actually adds the boron and the hydrogen across the same side of the alkene. So this is a syn addition product. And when you oxidize off that bromine, it does not change the stereocenter. You're not doing a substitution reaction. You're actually oxidizing at that bromine center, and it retains the stereochemistry of where the boron was. Okay, so if you add your boron hydrogen bond across that double bond syn, your alcohol is going to stay where the boron was. Okay. All right. Okay, so that's very important. But why is it syn? Well, it's kind of syn because of the nature of boron. Boron has trigonal planar geometry. It has an empty p orbital. Okay. It's kind of like the carbocation, where it's trigonal geometry and an empty p orbital. Okay, but boron doesn't need those extra valence electrons. It can be satisfied with just the 6. Okay, but the other thing about it is boron is less electronegative than carbon, and that less electronegativity of carbon tells us it's going to add differently across that double bond. Okay. So if we look at how the mechanism works, we have our empty p orbital start to arrange itself close to the 2 electrons in the pi cloud. Okay, so when it does this, it will start to move the boron and hydrogen closer to the double bond. And in the transition state, we're going to make and break bonds all at once in a concerted reaction. So the hydrogen is being attached to the carbon, the hydrogen-boron bond is breaking, and the carbon-boron bond is forming. That's why it's a syn addition. It happens all at the same time, okay? And so we end up making 2 new sigma bonds by syn addition. Okay. And there's a couple reasons for this. The first is electronic factor, okay? And the electronic factor is that boron is less electronegative than carbon, and therefore it has more of a partially negative charge on it during the transition state, which means the hydrogen has more of the more cation-like state, and it's going to align with the more substituted positive, partially positive charge on the more substituted carbon. So there's this electronic factor saying it kind of wants to be there. Because if it did it the other way, where's mine? There we go. So if it did it the other way, the boron is partially negative, and it's going to put the partially positive side on the less substituted carbon. That's what we expect it to be because it's Markovnikov products. But we're forming the less stable transition state. That less stable transition state is not favored and is much slower. So we add the boron to the least substituted carbon because of the more stable partially positive charge during the transition state. Now there's also a steric factor to it. If we look at it and start adding it the way we see it here, where the hydrogen is coming and it's being repulsed by these two methyl groups, the boron is only being repulsed by these two hydrogens. The boron is larger than hydrogen, and therefore this is energetically favored because the boron is not being repulsed by those two methyl groups. If we flip it around the other way, and we have the boron here and is now being repulsed by these two methyl groups, and this hydrogen is only being buffeted by these two hydrogens, that is not as stable because the boron's being forced away, and therefore the boron going to the less substituted carbon is sterically favored as well. So there's an electronic reason and a steric reason to put that boron on that least substituted carbon. Okay. And so, but then the next step is the oxidation. We have to make sure that we understand that when we do this oxidation, we are not doing a substitution reaction, okay? We are taking our boron and using that empty orbital again to transfer the hydroperoxide ion to that empty orbital, giving us our charged intermediate, which is very unstable. And so what happens is the boron-carbon bond breaks and this carbon jumps over without changing stereochemistry to give us the boron-oxygen carbon bond. Okay. So this is not very stable right here. We have the electrons from this carbon jump over here, losing the negative charge on bromine, getting back our neutral bromine, and kicking out hydroxide. Okay, and it'll do this every single carbon bromine bond. Okay, so once you have all of the carbon bromine bonds switched over to carbon oxygen bonds here, now we can have nucleophilic attack at the boron center and start displacing those as alcohols or as deprotonated alcohols. And then when we protonate them, they turn into the final alcohol. Okay. Because we're going from that boron carbon bond to that boron oxygen, from that boron carbon bond to that boron oxygen carbon oxygen bond, we do not switch our stereochemistry. Okay. So it's syn addition, and that hydroxide stays in that syn addition spot. Okay, questions on that? So let's see, we can add water, we can make alcohols 3 different ways now. We can do hydration, acid catalyzed hydration, halohydrin, it'll give you an alcohol, but it'll have a halogen in it. And now the hydroboration oxidation reaction. Okay, so the most important things to remember are you retain the stereochemistry of that syn addition. Okay, that syn addition is anti-Markovnikov. That boron is on the less substituted alkene. And when we do our oxidation, the alcohol stays on that less substituted and it stays in that syn configuration. Okay. All right. So in contrast, we can use a different material. Instead of using boron, we can use another material that is less electronegative than carbon. And in this case, we're going to use what we call mercury. And so it's called oxymercurization, demercurization. So we're going to add an oxygen and a mercury across that double bond. And then eventually we're going to clip off the mercury to give us our final product. Okay. So because our mercury is also less electronegative than carbon, we're going to see the mercury add to the least substituted side. Because the mercury is adding to the least substituted side, our alcohol is now on the more substituted side. Okay, so if we think about it, it's regioselective because the mercury always adds to the least substituted carbon, and then the alcohol adds to the more substituted carbon. But it's also stereospecific because it's a pure anti-addition. when you have the mercury coming in on the one side, the alcohol adds to the other side. And so instead of being a mixture, in the case of the carbocation, they add at the same time, but anti to each other. We do not form a carbocation. Okay. Now, once we have that mercury on there and we have our OH on there, we typically don't want the mercury on there. So we actually reduce it off using this sodium borane, sodium borohydride right here. And that gives us our oxygen on our more substituted carbon. And our hydrogen is taking the place of our mercury. Okay. So, does this mechanism involve a carbocation? It can't. It can't involve a carbocation because we would have a mixture of syn and anti-products. The fact that we only have an anti-product tells us we don't go through a carbocation. And it tells us that the mercury is going to add to the least substituted carbon. Okay. So what's the advantage of this reaction? Well, let's do it through the mechanism first, okay? So what's going to happen is our mercury is going to form this complex where it has two acetates on either side of this oxygenated mercury, right here. And then what's going to happen is one of these groups is going to leave right here, giving us a positive charge on our mercury. Okay, so now we have our nucleophile is our alkene, and our electrophile is now that positively charged mercury. Okay, so if we're bringing a positive charge in, then we're going to end up with a positive charge on our material here. And so what we're going to see is we'll have one possible resonance structure is where we form the tertiary carbocation. But the other more stable resonance structure is where the positive charge resides on mercury. Mercury is less electronegative. It's more able to stabilize the positive charge. And so if it shares across those two systems, it will be kind of like the bromonium cation. The positive charge is on the mercury, and that is a more stable resonance structure, and therefore it's most likely formed. Okay. So, but just like we saw in the bromine, they're not evenly bound to the secondary and the tertiary. The tertiary is going to have more of a partially positive charge on it, meaning it's going to be a better target for the incoming nucleophile. So the nucleophile comes into the more substituted carbon. That's why we get the, number one, we get the anti-addition because mercury is taking up the top of the molecule. And we have the nucleophile coming in attacking anti to the mercury, but at the more substituted carbon because those two bonds are not equal. There's more of a positive charge on the more substituted carbon, making it a better target for the nucleophile. So that's why we have the regioselective chemistry as well. The anti-addition and more substituted carbon. It's like, well, gosh, mercury is toxic. Why would we use this instead of the other one that already gives us the more substituted one, the acid catalyzed hydration? Well, we can use it to our advantage in certain situations. Okay. So, okay, I already talked about that. We can, okay, sorry, I skipped a slide. All right, so when we do the demercurization, we believe it happens through a radical mechanism, okay? And the reason we believe it happens through a radical mechanism is we do not see a carbocation form. We don't see any movement of a carbocation formation. And so what we think is happening is it's just reducing off. Now, typically there is not a stereo center on that. It's an acarbocarbon, so we really can't tell. But we believe that the demercurization is not stereospecific. It can happen anyway. And so unlike the one where we had the specific stereo center on the boron, where the the OH was on the same side where the boron was, the mercury just can leave and we end up with a hydrogen. Okay. But we know it doesn't go through a carbocation. Okay. The reason we know it doesn't go through a carbocation is because we do not see rearrangement products. Okay. So in the case of our material here, we can selectively choose which carbon we want this alcohol to be in. Okay. In the case of this alkene right here, if we do oxymercurization, demercurization, the mercury is going to go to this carbon here, which is going to give rise to have, no, sorry, that's wrong. No, the mercury is going to go to the less substituted carbon. The mercury is going to go here, right? Which means our water, our OH, is going to end up on this carbon here. This is our secondary carbon, okay? Because we don't go through a carbocation intermediate, it does not rearrange and it stays on that secondary carbon. However, if we used the dilute sulfuric acid, the acid catalyzed system, we do go through a carbocation. And that secondary carbocation that initially forms here will rearrange to be a tertiary carbocation, and we'll end up with our tertiary alcohol. Okay, so that's why we use mercurization, demercurization, because wherever the least substituted carbon is, the alcohol stays on that more substituted carbon than the alkene and does not rearrange. Okay, so if you wanted a secondary alcohol, the oxymercurization, demercurization might be the best choice. Now let me kind of drive that home with this slide here. Okay, I have this alkene and I have a whole bunch of it, but I want to make a few different alcohols for some research project I'm doing. And I know I want to make a primary alcohol, I know I want to make a secondary alcohol, and I know I want to make a tertiary alcohol. All I have to do is choose my reagents to figure out which is the best one to use. So if I'm going to make a primary alcohol, I have to use the hydroboration oxidation reaction, because the boron is going to add to the least substituted carbon, and we're going to oxidize that boron off, giving us that least substituted alcohol. So we have to use this to get our primary alcohol. Okay. Now let's just go, let's just hit it with acid and water and hope for the best. Well, it's going to form a carbocation. The carbocation is going to be here, but then it's going to move over here because that's more stable. And our major product is going to be our tertiary alcohol. Okay. So we have very specific way to get our tertiary alcohol. We have a very specific way to get our primary alcohol. The only route we have for our secondary alcohol is the mercurization, demercurization. And that's because our mercury is going to add here to the least substituted carbon, which puts our OH at that secondary carbon. We don't form a carbocation, and so it stays on that secondary carbon. And that's the only way to get to our secondary alcohol from this alkene. Okay, so when I started this story at the beginning of the lecture, it was we are looking for regiochemistry, we are looking for stereochemistry, but we're also looking for specificity of product. You have to choose one of these reagents to get the product you want. So it's very important to keep that in mind on what the mechanisms are and what the products could be. All right, questions on the three alcohols? Okay. We're coming to a close here. All right. Yeah, I can do this in 5 minutes. Another thing we can do with an alkene is not just make it into an alcohol, but let's make it into an ether. In this particular case, we're going to make it into an oxacyclopropane. Most people know them as epoxies, okay? An epoxy is a strained ring system that we can attack with other nucleophiles later. But the way this works is we're going to use what we call a acid, which is a carboxylic acid with an extra oxygen in it, okay? And when we do that, we're just going to add an oxygen across that double bond, and that's how we form that nice little ring. Okay, so let's kind of look at that acid a little bit here. If you had just a normal carboxylic acid, OH, we're going to have a negative charge on this oxygen here because we're going to have that partially positive charge on that hydrogen, right? But when we add that extra oxygen, one of these oxygens now becomes electrophilic, partially positive, okay? Our alkene has electrons. It's nucleophilic. So what's going to happen is that that alkene is going to react with that extra oxygen to generate our addition product to give us our. Now, it always requires one of these peroxy agents, like a peroxide, or most of the time it's going to be a per acid. Per just means you have an extra oxygen in it. So peroxyethanoic acid is actually acetic acid with an extra oxygen. But the most common reagent we're going to use is what we call MCPBA, metachloroperbenzoic acid. Metachloroperbenzoic acid. It's soluble in a lot of things, and it makes this reaction go very, very well because you can weigh it out very precisely as a solid. Okay. So when we do this, we want to do this in a solvent that doesn't react with the peroxide. And so that's why our solvent here is dichloromethane. Okay. It doesn't participate in the reaction. It's just a good solvent that does not react with that. Okay. So what's the mechanism? Well, I showed you that there's a partial positive charge on one of those oxygens, and we know that the alkene is a nucleophile. So the thing that's going to happen is it's going to come, and kind of like when you're forming the bromonium cation, or kind of like when you're forming that mercury cation, it's going to add across one side of the bond. But notice when we do that, it kicks out the, okay, let me pull this up here. We have the electrons that were bonding to the oxygen kicking in to form a bond with carbon. Our other carbonyl from the carboxylic acid can reach out and pull away the hydrogen with its extra electrons. And the electrons from the double bond can form a new sigma bond with the oxygen. And then the last two electrons leave to form the new carbonyl on the leaving product. So let's look at where our electrons are now. The alkene electrons are used to make one of the sigma bonds with the oxygen. The oxygen-hydrogen electrons are used to make the other sigma bond, and we have a neutral species. We have a stable species, and we have completed our reaction. Okay. And of course, we end up with the alcohol at the end. Okay, so let me just do the one last slide and I'll let you go. So it turns out that our epoxy formulation is stereospecific because it adds syn. It's going to add to this double bond all at once. So that means if you started with a cis alkene, you're going to have those two R groups in the same proximity as they were before. They're going to be next to each other, giving you the syn epoxy product. If you started with them opposite each other, they're going to stay opposite each other because, again, we're adding across just the one side of the double bond, and they stay in the same proximity. They do not rotate, they do not change, so it's a very stereospecific reaction. All right, I'm gonna stop there, and because it's 120, right? Yeah. Do we stop at 120 or 140?
150.
150, all right, great. I have one more slide. Okay, I don't know why I thought it was 120. Okay, so that's another cool reaction we can do with alkenes, right? So we're, again, taking the two electrons from the alkene and making some sort of sigma bond with something else. In this case, we're making two sigma bonds with the same oxygen. Okay. So what else can we do? Okay. Well, we can take our alkene and reduce it all the way down to an alkane. Okay. So how would we do that? Well, we would do that what we call catalytic hydrogenation, right? And remember, we talked about catalytic hydrogenation when we were talking about stability of alkenes and how much heat they gave off. Okay, well, now let's talk about the reaction itself. Okay, in catalytic hydrogenation, you have hydrogen gas and some metal, palladium, platinum, nickel, rhenium, something like that. Okay, now Because hydrogen has a nonpolar bond, you have to activate that bond. And you activate that bond by having it adsorb to the surface of your catalyst and break those bonds. So now we have activated hydrogen atoms. Okay. Now you have activated hydrogen atoms at the surface of a solid, right? Now your alkene will come and sit down on top of that and transfer 2 hydrogens. Okay. So because it can transfer them one at a time or 2 at the same time, it does syn addition. Okay. Both hydrogens add to the same side of the double bond. Okay. Without that catalyst, it's not polar bond, it wouldn't react. With the catalyst, it sits down on the surface and gives us our syn addition. Okay. Questions on catalytic hydrogenation? It just takes it down to an alkane. It's not as fun as making an alcohol or a halohydrin. All right, so now I'm going to give you a summary of our stereochemistry and which reactions give us syn addition, which reactions give us anti-addition. Okay, so the ones that go through that carbocation give us a mixture of our syn and our anti. Okay, this is in the wrong place. These. Okay. Okay, yeah. So if we think about that, in the ones that form the carbocations give us a mixture of syn and anti, and that's the hydrohalogenation reaction and the acid catalyzed hydration reaction. Let me see. The oxymercurization, demercurization is regiospecific, but not stereospecific. So the reactions that only give syn addition are hydroboration. We have that 4-membered transition state. Catalytic hydrogenation, 4-membered 4-membered transition state, and our syn dihydroxylation, which I haven't got to yet. We'll get to that soon. Okay, the reactions that only do anti are the halogenation and the halohydrin reaction, because remember, we're blocking one whole side of it, so the nucleophile has to come to the other side, so it must be anti. Okay, so with that in mind, now we've got to figure out about what are the dihydroxylation reactions. Okay, well, before we talk about the dihydroxylation reactions, let's talk about the oxidation states of carbon. Okay, so the lowest oxidation state possible for carbon is when it has 4 hydrogens bonded around it, so it's methane. Methane is our lowest oxidation state, and it has the greatest number of its own electrons. Okay, as we move up and start losing these electrons to other more electrophilic atoms, it becomes more and more oxidized. So you can think about that as, oh, we're going from an alkane, the first new bond to an oxygen is our first oxidation. And then if we have 2 bonds to oxygen, oh, that could be an aldehyde or a ketone. That's another oxidation. And then by the time we get to carboxylic acids, we have 3 total bonds to oxygen, and that is even more oxidized. Now, the only way to get even more oxidized than that is to have 4 bonds to oxygen. Okay. But, you know, you don't have to imagine it. You don't have to kind of say, well, is it more or less? We can actually put a number on it, okay? And the way we put a number on it is we give values to different things. So we give a -1 to each carbon-hydrogen bond, okay? We give a 0 to each carbon-carbon bond, and we give a +1 to each bond to something more electronegative than carbon, nitrogen, oxygen, halogen, okay? So let's do the math, okay? So if we have methane, I said that's the lowest oxidation state possible. We get a -1 for each of those hydrogens, meaning our oxidation state is -4, okay? So that's our low end, -4. You cannot have any more bonds to hydrogen than 4, so that must be our lowest one, okay? And when we think about it in the sense of valence electrons, we had 4 valence electrons, but now it has 8 because of the 4 bonds with the 4 polar bonds with hydrogen. Okay. Now let's oxidize it a little by taking it into an alcohol. And if we look at this carbon, if we look at this carbon over here, we have 1, 2, 3 bonds with hydrogen, so that's -3. We have a bond to carbon, that's 0. So the oxidation state here is -3. But let's look at the other side, right here. We have a bond to carbon, which is 0. We have a hydrogen, which is -1, a hydrogen, which is -1, and an oxygen is +1. Okay, that means our net oxidation state is -1. It started out as -4. We started adding carbons and an oxygen to it. We've gone up to a -1. Okay. Well, let's get a second bond to the oxygen. Go down here. Okay, so each of those bonds to oxygen counts. So we have, for this carbon here, we have a -1 for the hydrogen, a +1 for the oxygen, a +1 for the oxygen, and a 0 for the carbon, giving us a net oxidation state of 1. So an alcohol has an oxidation state of -1, but an aldehyde or ketone will have an oxidation state of +1. So how far can we go? Okay, well, we can go to 4 bonds to oxygen in something like CO2. Okay, in the case of CO2, we have each oxygen gets a +1, giving us a net oxidation state of +4. So our range available to us in organic chemistry is an oxidation state of -4 to an oxidation state of 4, +4. Okay, so now that we know a little bit more about the oxidation state, we can look at additional chemistry that we can do with an alkene. And in this case, we're going to do a dioxylation of these materials, or making diols of the materials. So the first thing I want to talk about when we're talking about dihydroxylation, adding 2 alcohols to the system, is the material called osmium tetroxide. Okay, osmium tetroxide, it's a nice little planar molecule, and it has 4 oxygens on it. And when it goes, it reacts with alkenes to give what are called vicinal diols, meaning you have an alcohol on the 1 carbon and an alcohol on the 2 carbon. That's vicinal diol. Okay, so the way in which the osmium tetroxide reacts with the alkene is you actually have it add across the double bond, giving you this cyclic intermediate. Okay, that's actually isolable. You can make that complex and it's stable. However, if you are going to have it be the diol, you have to oxidize off the osmium to generate osmium, and reducing off it to create osmium and our diol. Notice that this is a syn addition. Okay, because it's going on the same side, both oxygens are on the same side, it is a syn addition. Okay. All right. So, and we've changed the oxidation state of osmium from +8 to +6, but we've changed the oxidation states of these from -1 to 0. We've gone up in oxidation state. Okay. So, unfortunately, osmium tetroxide is actually really, really toxic. So what they figured out is they can do it catalytically. Okay, so you use just a hint of osmium tetroxide, but when it goes to osmium in its after it's reduced off, you can reoxidize your osmium using an oxidizing agent called N-methylmorphin N-oxide. So if you look at this, you have a methyl group on our methyl group on our nitrogen. This ring here is called morphin, and then it has an oxygen here. This oxygen is used to reoxidize the osmium tetroxide to the osmium to osmium tetroxide, and therefore you regenerate your reactive species by adding equivalent 2 or more equivalents of your NMO, or N-methylmorphin N-oxide, so that you only have to use a tiny bit of the toxic material to still get this diol. Okay, questions on osmium tetroxide? Do you see why it's a syn addition? We're forming that 5-membered isolable product, that osmium ester, and then when we oxidize it off, we get the diol staying in the same place. Okay. All right. In the case of permanganate, we're going to see that same thing where we're going to have that manganese tetroxide is going to form that same kind of intermediate. However, because the manganese, potassium permanganate is more, can oxidize more strongly, it's a stronger oxidant, that's what I'm trying to say. Because it's a stronger oxidant, it's only useful if we do it in very cold temperatures in neutral conditions. Okay? But most of the time when we use potassium permanganate, we use it under basic conditions. Under basic conditions, it doesn't stop at the diol. Under basic condition, it actually breaks the double bond apart. And when it does that, it oxidizes both of those carbons all the way down to carboxylic acids. So it's a great way to take an alkene and turn it into two different carboxylic acids, or in the case of this one, two carboxylic acids at the end of the same chain. So your reagent of choice for making vicinal diols should be that osmium tetroxide. Okay. So questions about the difference between the potassium permanganate, even though it initially adds syn, it just continues to over-oxidize the system. So what else can we do with this double bond? Well, we can break that double bond using a different reagent. We can use ozone, okay? So in the case of ozone, it's a very specific reaction because ozone, turns out if we draw all of its resonance structures, it has a separated charge. It has a negative charge and a positive charge, and it kind of moves around. And so sometimes in one of its resonance structures, if you have the charges spread out as far apart as possible, we have what we call a 1,3 dipole reagent, meaning we have a positive side, a negative side, and those are permanent charges, and they're on the two ends of the molecule, okay? That gives rise to its reactivity. So we're gonna have to remember this resonance structure when we talk about the mechanism of the reaction. But let's talk about the outputs of the reaction. If we do the reaction where we have a reductive workout, we don't use an oxidizer. In this case, we're using dimethyl sulfide. In this case, the sulfur picks up the extra oxygen of the ozone, okay? And I'll show you that in a minute. So what we end up doing is we end up actually clipping the double bond apart, creating a double bond to oxygen on one of the carbons, and a double bond to oxygen on the other carbon. In this particular case, we'll end up with a ketone on the one side and an aldehyde on the other. Okay. But that only works with this dimethyl sulfide. What if we didn't have something to take away that third oxygen of ozone? Well, we'd clip it again right here, and then we would have the ketone form, but then this aldehyde would be oxidized to the carboxylic acid. Okay. So workup is everything. If you want to create the aldehyde, you need to do the reductive workout. If you don't care about the aldehyde, you want the carboxylic acid, you do an oxidative workup. So what's the mechanism? Well, I said that 1,3 dipole structure of ozone is very important. And it's very important because we have a negative side here. We have a pair of electrons in our pi bond here. Where is it? We have a pair of electrons in our pi bond, and we have a positive charge. So we have what we call a concerted 1,3 dipolar addition. The electrons from the negative side come and attack this carbon. The electrons of the double bond attack the positive charge here, and we form this cyclic intermediate here. Okay. So the problem is this cyclic intermediate is not very stable. Okay. So what it's going to do is it's going to try to break apart and change into a ketone, but then we notice we have this dioxygen species, this peroxy anion here. Well, it's still in close proximity to that ketone. So we have a nucleophilic side, and we have a partially positive ketone here. It's going to attack that, and we're going to end up making a 5-membered ring that is more stable than having these 3 oxygen bonds, these three oxygens bonded together, gives you this material here. So this is the actual intermediate that can be isolated because it's more stable than this isomer. Okay. So now we can do the workup, okay? So we form this right here. We have a total of 3 oxygens. If we don't get rid of one of those oxygens, we're gonna have an oxidized material. If we do get rid of one of those oxidized, it's going to give us a different material. Okay. So let's start looking at what we can do to get rid of that oxygen. We have 2 different reagents we can do to have a reductive workup. We can use zinc metal, and it goes into zinc oxide, or we can use the dimethyl sulfide. The dimethyl sulfide ends up becoming dimethyl sulfoxide. The oxygen is being transferred to the sulfur. If we have something for this third oxygen to transfer to, in this case, the zinc or the sulfur, we can end up with the aldehyde. Okay. So if it's a substituted tri-substituted alkene, we're going to end up with a ketone for half of it, an aldehyde for the other half, and those are the electron products. If we have a di-substituted alkene and both of the substitutions are on the same carbon, we'll actually get a ketone, but we'll get formaldehyde because there's 2 hydrogens on this side here. If we use the reductive workup and transfer that oxygen to the other species. But what if you don't use that? Well, we don't get rid of this extra oxygen and it ends up staying on our substrate and we end up with the carboxylic acid and it'll lose, let's see, the electrons kick in here to form your carbonyl, the hydrogen gets transferred to the oxygen there, and we end up with the carboxylic acid. And if you do that with a di-substituted alkene here, we end up getting a formic acid. So it's still a carboxylic acid, it just has a hydrogen there. And so it is going to over-oxidize one of the sides of the alkene to give us our carboxylic acid. Questions on that? So whenever you see an ozonolysis thing, you've got to think, okay, what's the second step? That's going to tell you what your products are. First thing it's going to do is cut that double bond in half. The second thing it's going to do is either reduce it or oxidize it. Okay, so there's a kind of an easy way to think about what your products are. The idea is if you just cut it in half and start adding oxygens to this, that's going to tell you what your products are going to be. Okay, so in the case of cutting this in half, we have a hydrogen here. So we have to look at what are we reducing or oxidizing. If we're cutting that in half, we're going to end up with an aldehyde on one side and a ketone on the other, and that'll give us our 2 products here. But if we have an oxidizing step, we have to think, okay, the ketone side is going to stay the same, right? But we're going to oxidize this aldehyde to give us our carboxylic acid as our final product. The ketone's the same, but the oxidation gives us our carboxylic acid instead. All right, questions about ozonolysis? Okay. All right. All right, great. Okay, so I said before that the addition of HBr or HCl across a double bond is a Markovnikov addition. We're going to put the hydrogen on the more substituted carbon. Okay. But what if you wanted to do it the other way around? Okay. If you want to do it the other way around, you have to change the mechanism. Okay. If you go through the carbocation intermediate, you will form the more stable carbocation. That more stable carbocation will end up on will end up with the halogen. Okay, so if we change the mechanism to be something other than a carbocation, we can get the reverse product. So in the case of HBr, if we use peroxides, and peroxides are any organic or inorganic compound with an oxygen-oxygen bond, they break apart homolytically. Each oxygen takes 1 electron with it, and it generates a radical. Okay, When we generate the radical, we're not generating a carbocation, and we get the anti-Markovnikov product. Okay, so radicals have the reverse stability of carbocations, okay? Because of they're closer to carbanions than the carbocations. And it's because they're stabilized like carbocations by hyperconjugation. Okay? So instead of having an empty orbital, we have one electron in that p orbital. That one electron in that p orbital starts pushing the other groups away. It's not trigonal planar anymore. But it's not all the way to a tetrahedral structure as if we have a lone pair on there and a carbanion. Okay? So what that means is that with that one half-filled orbital, it is stabilized by hyperconjugation by the adjacent carbon-hydrogen bond. Okay? So that means if we have an adjacent bond there, it's going to help stabilize. Now, what does that mean? Okay. That means wherever you form your radical, it's going to stay there, okay? Because radicals do not rearrange like carbocations do, okay? So in the case, if we formed a secondary carbocation, it'll immediately do a 1,2 hydride shift and give us our tertiary carbocation. However, if we form our radical on our secondary center, it stays on our secondary center, which means that radical then will react with something in the solution to give us our secondary substitution product, or our secondary product reacting with that radical. Okay. So what does that mean for hydrobromation? Why is it anti-Markovnikov? Well, let's look at the mechanism. Okay. So in the case of all radical reactions, the first thing that has to happen is what we call initiation. Okay. And initiation happens when you break that oxygen-oxygen bond homolytically, meaning that one of them goes away with one electron, the other one goes away with one electron, and we have basically two equivalents of single electrons. Okay. The next thing that happens is that single electron on oxygen will take the hydrogen from, a hydrogen and one electron from the bromine, giving us our alcohol here and our bromine radical. It's not an amide. It has 7 electrons. It's neutral. It has a highly reactive bromine radical associated. So the next thing that can happen is we have what we call propagation, meaning that radical is going to react with one of the electrons of the alkene to form a new radical. And in the case of this right here, we have the formation of a tertiary radical. And if we do the same thing and put one of the electrons to give it here, we'd have a secondary radical. Okay, so what is the trend here? Okay, the trend here is that, oh, did I misspeak? That radicals and carbocations have the same trend, okay? A tertiary radical is more stable than a secondary radical, and it's more stable than a primary radical because of hyperconjugation, just like carbocations. I think I said it was the backwards, but it's not. It's the same as carbocations. Okay, so if we form this intermediate here, this is going to be the more stable tertiary radical. This is going to be the less stable tertiary radical. Okay, so what can happen is we're going to form a little bit of one, a little bit of the other, but then we have to finish the reaction. Okay, to finish the reaction, we have to either transfer a hydrogen from the hydrogen bromine to the final radical to give us our anti-Markovnikov product, or we can actually have it attack with another radical bromine to finish the reaction and end up with a dibromo compound. But notice if we had this species, we'll end up with the anti-Markovnikov product. If we have this species, we'll end up with the Markovnikov product. Okay. So if the anti-Markovnikov product is the right one. That means our tertiary radical here is the more stable and is more likely to form, meaning that our termination step here is when we form our new hydrogen bond. We abstract a hydrogen from another equivalent of HBr to get our final product. And then eventually we have to terminate all radicals by either combining all of the alkanes, all of the radicals we just formed, or all the bromine radicals together to get to our final product. The key here is that the tertiary radical is more stable than the primary radical, and the bromine is added first. So that means the bromine is going to be added to the less substituted carbon, and the hydrogen is going to be added to the more substituted carbon. Okay. So we've been able to flip the location of there by changing the mechanism. We changed from a carbocation mechanism that gives us the Markovnikov product to a radical mechanism that gives us our anti-Markovnikov product. But they both rely on the idea that the tertiary radical is more stable or that the carbocation is more stable. But in the case of the carbocation, we're adding the hydrogen first. In the case of the radical, we're adding the bromine first. And so it switches the regiochemistry. Okay. So that brings us to the overview of what we've learned here. Okay. We learned hydrohalogenation is a mixture of syn and anti. We learned that hydration, acid catalyzed hydration, is a mixture of syn and anti because they go through carbocations. Halogenation is always anti because of the formation of that three-membered ring. The halohydrin reaction is anti because of the formation of the three-membered ring. The hydroboration is not only syn, but gives you the primary alcohol out of it. The oxymercurization, demercurization gives you a mixture of the two, but for a different reason, not a carbocation. When we do our osmium tetroxide, we always get syn addition and produce an alkene. When we do hydrogenation, we get syn addition and get an alkane. And if we use permanganate, we break the double bond completely. Okay, all right, that brings us right about to 150, and we'll start with module 8.2 on Monday, alkenes.
Thank you.
Right.
Thank you.
Go ahead and
Dr. Irvin, I have a question.
yes.
On Top Hat, it says that Module 9 is due the 19th, but on Canvas, it says that Module 9 is due the